So, good evening, everyone. Welcome to the NPTEL online certification course for problem solving and doubt clarification on the topic water and wastewater treatment. And we are presently in week 3 now. And as you all know, the course instructor is Professor Bhanu Prakash from IIT Roorkee, and I am Akash Shah, one of the teaching assistant for this course. And I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. Okay, so as you all have, I think, gone through the contents of week 3. So in week 3, we basically discussed regarding the remaining water quality parameters. We talked about total suspended solids and pathogens. And then we moved on to the preliminary treatment of wastewater. We learned about the basic principles, what are bar screens and grid chambers are used for as a preliminary treatment. And then we moved on to primary treatment, where we learned about the basics of sedimentation, what are the different types of settling starting from discrete and flocculent settling, and what how to design the primary sedimentation tank. Okay, so we have started with the design, and we saw basically the preliminary and the primary treatment. Okay, in the coming classes we will learn more about the secondary, tertiary, and the advanced processes for wastewater treatment. Okay, so today I'll be discussing uh, regarding mostly contents of week 3, all these concepts. I have some numericals as well as some multiple choice theoretical questions, so we'll solve them one by one. If you have any doubt at any point of time, you can raise your hand, or like in the chat box you can point out, or you can unmute yourself or speak. Okay, you are free to do anything. And please, while we are discussing the questions, please answer. Okay, whatever you are able to guess, you want to guess anything, you want to try that question in any way, you just write it in the chat box or unmute and speak. It will be, we should make it interactive rather than I keep on speaking. Okay. So the first question, it says that what type of settling do the blocks A, B, C, and D denote in the figure below? So we have a kind of a settling tank where we have differentiated into 4 blocks: A, B, C, D. There, these are nothing but various zones. So we have to tell me what type of settling do these blocks represent. So go through the options. So we have something called as zonal settling, then we have flocculent settling, we have discrete particle settling, and we have compression settling. So based on your knowledge, please try to answer. It is very direct. And then we will discuss about each of the settling one by one, just roughly, not in full detail, because every detail is given in the week's content. You can go through. Any idea? Anyone? B. Okay. I think option B is. Anyone else with any other answer? C. Okay, I think most of you are confused in this. Okay, so we'll discuss. So actually, yeah, this is the correct answer. So the correct answer is D actually. So we will so A part represents the discrete particle settling, then the flocculent settling, then C is the zonal settling, and D is the compression settling. So we will discuss it. So what happens is, so first is the type 1 settling. So type 1 settling means discrete particle settling. So here what happens, the particles will individually settle down and one particle will not interact with the other particle. Okay. Okay, so this is the main criteria. So most of the like suppose grid chamber and all are there, so there this discrete particle settling will happen. And as we have also seen about the Stokes law, it is mostly applicable in only this type of settling. Okay, so individual, so always remember the particle will settle individually and there will be no interaction between any of them. Okay, one particle will not influence the settling of other particle. So these are the two main points. Then flocculent particles. Flocculent particle settling means the particle will change their mass and shape with time. So what happens is like these particles tend to agglomerate with each other. They will come closer, they will interact, they will grow in size and then settle faster. So as you all know, as the size will increase, the particle settling velocity will increase. Okay. So that is why we do generally what we do in some cases, in some reactors, we will add some coagulants. Okay, you might have heard about coagulants. Okay, so these coagulants will help in bringing these particles close to each other so that they will agglomerate with each other and then increase in size and then settle down. So that is what is happening. If you see the figure B closely, you can see that some particles are getting connected with each other. Okay, whereas in A block, every particle is individually present. They are not interacting with each other. Then the next is the hindered or zone settling. That is the type 3 settling. So here the mass of the particle tends to settle as a unit with individual particles remaining in fixed positions with respect to each other. Okay, so in zones it will settle down. So particles will be in fixed position to each other. Suppose one group is here, one group is here in particular zones. So this we can see uh, basically in any kind of secondary sedimentation tank. Okay, in any kind of secondary sedimentation tank, we can see this kind of settling. Now, the last one is the compression settling. So here what happens, the concentration of particles that is present here is so high that it will compress each other. Okay, it will compact, it will compress each other, and in that way it will be very close. The concentration will be very huge. You can see in the D block, the compression will happen and then the particles will settle down with compression. So this happens in some kind of in sludge reactors or sludge digestion reactors. In those tanks, this kind of settling happens. Okay, do you have any doubt in any of them? Is it clear to all of you? Okay, okay, so we'll move to the repeat type 3. So type 3 means the particle, okay, you just imagine that the relative positions of particle is fixed. Okay, they are traveling together but they are not compressing with each other. Compression means the relative distance or the relative positions will change and it will compress each other. What is happening, that is happening in type 4. But here in type 3 it will not compress each other, but as per zones it will settle in layer by layer. Okay, am I able to make it clear? Okay, yeah, so there is a minute difference between 3 and 4. So just, so it basically the concentration of particles will govern this. Okay, based on the concentration and what kind of, if you are adding some coagulants or not. Okay, how the particles are interacting with each other based on that, right? So as we move from one zone to another, the concentration of particles is increasing. And in type 4, it is so much that it tries to compress each other. Okay. Next question. In sedimentation with coagulation, generally the detention period is dash than that of a plain sedimentation. So I just discussed about coagulation. So which kind of settling will happen here? Can anyone tell me? Type 1, type 2, type 3 or type 4? So when we have coagulation, what kind of settling will happen? Can someone tell me? Type 2, yes. So if type 2 settling is happening, yes, type 2 will happen. So if type 2 settling is happening, will the detention time. So just uh, think in think in that aspect, that suppose detention time is what, I just told you that if coagulation is happening, the particles will come to close to each other. Okay, the size will increase. Okay, the size of the particle will increase, and if the size is increasing, the settling velocity will also increase. So if settling velocity is increased, what about the time? Okay, here we are asking about the detention period. Detention period is nothing about the time required for the settling. Okay, so if particle settling velocity is increasing, what will happen to the time? How much time will be required? It will be required more or less? Less, right? So definitely the answer is less. So the addition of coagulants causes the particles to clump together into larger flocks, which settle faster, requiring less time to settle in the sedimentation tank. So this is the normal behavior of the particle. Next one. In natural flow conditions, an unpolluted river would likely to have, so we are talking about an unpolluted river. So what will happen, how the dissolved oxygen will change in summer and winter. Okay, will it be more in summer or more in winter, or it will be same in whether it's summer or winter? Okay, so what do you think is going to happen? Just think about it and try to answer. Apart from that, is there anyone who has joined this class for the first time? Is there anyone who has joined this class for the first time? Okay, so I will just I will just share a link. Okay, so you please fill your details in this link. Yeah, so Faizan and I think one more Manish. Okay, so you both please just fill your details in this link. It's a Google spreadsheet. I will pin this also. So if I want to give any information or any resources, I will use the mail ID. So just I want your mail ID. Okay, apart from that, okay, you have answered it as B. So less dissolved oxygen in summer. So that is absolutely correct. So less dissolved oxygen will be there in the summer and more will be in winter. So why does it happen? Because the solubility decreases as the temperature increases. Okay, so the major thing is that the warmer water requires less dissolved oxygen to reach 100% saturation than the cooler water. Okay, so just think that the water will reach 100% saturation. Okay, so till that time only it will allow the oxygen to be solubilized. Okay, it will take oxygen up to that time. So it needs lesser water, lesser dissolved oxygen to reach that 100% saturation. Okay, and also you can remember that the solubility decreases as the temperature increases. So that's why warmer uh, water will be having lesser DO in summers. Okay, so that is what I wanted to discuss for this question. Now we'll go to the next question. Okay, so it's a small numerical. So it says that in addressing the treatment of a daily water flow of 1200 meter cube in vertical direction, a municipal corporation has identified specific parameters for circular settling tank. The tank's diameter is estimated at 10.78 meters and the depth of 4 meters. So we have the volume, okay, and the daily water flow is given, and we also have the diameter and the depth. Now we have to determine the overflow rate or the surface overflow rate called as SOR for this circular settling tank designed for the removal of discrete suspended particles. Okay, very direct question. I think you can solve it. So please take a minute to solve and let me know the correct answer. So you have to find out the surface overflow rate. So please take a minute and try to answer this question. Okay. Yeah, Faizan. So I think your answer is correct. So others have, are you not able to do it? Okay, so we will quickly see how to do it. I'll try to solve. Very simple. So this is question number 4. Okay. So first, what is SOR or surface overflow rate? It is nothing but the discharge Q divided by the top surface area. Okay. LB, or I can just write it as surface area. Okay, so what is Q? So it is given that daily flow of this much volume. Okay, so Q will be nothing but that same, because it is given per day. So Q is 1200 meter cube per day. So that is given. Now surface area essay, it is a circular area, so it will be pi by 4 into d square. So that is nothing but pi by 4 into 10.78 square, which is 91.27 meter square, right? So my surface overflow rate will be 1200 divided by 91.27. Okay, so this will be equal to 13.14 meter per day, so which is approximately equal to 13 meter per day. Okay, very direct. So always remember, when we are calculating the SOR, suppose if this is your tank, I will try to make a 3D picture. Suppose this is your tank in 3D. This is the length. Okay, this is the length. This is the height, or you can say depth, height or depth. And suppose this is the width or breadth. Okay, so whenever we are calculating the surface overflow rate, we have to take this area, this top area. Okay, so always the surface area for surface overflow rate will be L into B. Or I can say, if it is a circular thing, suppose this is a circular tank is there. So if this is the diameter D, this is the height H, so surface overflow rate will be this area. So that's why I did pi by 4 into D square. Is it fine? For circular will be pi by 4 into D square. Is it clear to all of you? Because you may make a mistake, you may take maybe this area, okay, or maybe this front face, this area will, may someone will take. Okay, so don't make these mistakes. Is it clear? So the same thing, detailed solution is given here. Next question. Microbiological examinations of water samples are usually based on MPN tests for the detection and numeration of indicator organisms rather than that of pathogens. So this is statement A. Statement B says the identification of pathogens in water is both time consuming and difficult. So you have to say whether both of A and B are true, or one is false, or one is the correct explanation of the other. So based on that you have to answer. So please try to answer this question. So it is talking about the microbial examination. So whenever we want to find out what is the how much microorganisms are present in the water, okay, to judge the quality of the water, we have to do NPN test, okay, which revolves around the detection of some kind of coliform bacteria, okay. And next it is showing that the identification of pathogens is very time consuming and difficult. So you have to tell me whether these statements are true or false, or how is it related to each other. C. A is true, B is false. Next is A. Both are true and B is correct explanation of A. Okay, any other answer? You think B? Okay, so first of all, when we try to do any microbial examinations, so tell me what do you want to find out? We want to find out pathogens, or those are not pathogens. What we want to find out? Can someone tell me? In drinking water, to judge the quality, what do you want to know about the pathogens or non-pathogens? Pathogens are basically disease causing microbes. So we definitely want to know about pathogens, okay. But it is true that finding about these pathogens will be very difficult, okay, and it will be time consuming. And also while finding about these pathogens, there are high chances that you may also get infected. Okay, so that is another concern which I am not considering now, but it is very time consuming to find about the pathogens. So what we generally do, we take some indicator organism, or we call it as coliforms, okay, and these coliforms are present wherever these pathogens are present. So these are harmless. These are basically harmless, and these are found in huge amount. Okay, so the more pathogens will be there, the more coliforms will also be present. Suppose one of the coliform is E. coli, Escherichia coli. Okay, so finding out the presence of these uh, coliform or indicator organisms is rather easy with the help of NPN test. So that's what is said in statement A and B. So both the statements are correct, because for microbial examinations we want to find out pathogens, but these finding out them is very difficult and time consuming, and also some health implications are there. So what we do, we try to find out the presence of coliforms, which is relatively easier, okay, with the help of the NPN test. So NPN means most probable number. It's a kind of probabilistic technique. Okay, so we will discuss it later. So that's what is the answer. So both option A and B are correct. Is it true? Is it clear to all of you? Sorry. Is it clear to all of you? Right? Okay, so we'll move forward. Okay, so the figure below provides insight into the variation of a city population based on the ratio of peak hourly to average flow. Okay, so they are calculating the ratio of peak flow by average flow. So you have to tell me whether AB denotes a small community or a large community, or BC denotes a small community or large community. So based on the ratio of my peak flow to average flow, so what is it called? Peak flow to average flow. What is that factor called as? Anyone knows? What is the factor of, what is the ratio of peak flow to average flow? It is known nothing but as peak factor or peaking factor. Okay. So based on the peak factor, we can tell that whether it's a large community or a small community. Any idea? Okay, so let me help you out. If, suppose I am making a graph. Okay, so here is my flow. Okay, here is time. So from 0th hour, 0, 1, 2, 3, like that up to 24 hours, I have marked the points. So suppose first the flow was this much, then it increased like this, then it decreased, then again it increased, then it decreased, then again it increased, like this, the flow is there. Okay, so one will be my peak flow. Suppose this is the maximum flow, and there will be some flow which is my average flow. Suppose this is my average this much, and this is my peak. So we want to find out the ratio of peak by average. So now the question is asking that whether this factor will be more for a small community or more for a large community. Whether this ratio will be more for a small community or large community. So this is what is the question. Now, are you able to answer? And one more thing, just imagine, suppose there is a town where there are only 10 people. Okay, and in other town there are some 1 lakh people, right? So what do you think, the variation will be more in the case of 10 people, or the variation of peak flow to average flow will be more for 1 lakh people? Where will be more variation, you can think about? So see, you are thinking in terms of, you are saying that average out, but just think that suppose in a smaller community, the chances of getting high and low will be very, will be too much. Okay, you cannot, like, uh, if you ask a particular suppose there are 10 you in a class, if you if you know about this kind of graph you have seen, so mostly things tend to fall in between the average. Okay, so most of the thing will average, whereas the extreme things will be very less. Okay, so whenever you have lesser people, the chances of variation is very high. because the flow pattern and all you cannot control. Okay, whereas when there are too many people, everything will try to average out. So the chances of variation with respect to your average will be generally lesser. Am I able to make it clear? So what I'm saying is, when you have a small group of people, the chances of variation of highs and lows from your average will be more. Okay, whereas when you have a larger population or a larger community, this variation of highs and lows will be smoothening out, and everything will be trying to take place within the average, like near the average thing only. Okay, so the peak factor will decrease. So that's what is the question. So when we have a smaller community, like like BC, okay, the peak factor will go down. Whereas if we have a, sorry, the peak factor will go up. And when we have a larger community, the peak factor will go down. So that's why AB denotes a smaller community and BC denotes the larger community. Is it clear? Okay. So just think about it more in terms of some other analogy. Uh, because suppose try you are taking any normal random survey about anything. Okay, you are asking some particular question, like to what should I say, like to guess a number between 1 to 100. You are asking 10 people, then you will find that the variation between the answer will be too much. It can be very high. Okay, whereas when you ask for about some 1 lakh people, the variation in their answers will be comparatively lesser. It will be more or less in between the average. Okay, so in normal surveys we can see this trend, and that's what happens in general usage of water or whatever in that case. So just try to think in some other analogy. So the ratio of peak hourly flow to average flow, often called as the peak factor, generally decreases as the population increases. Now next question. So we have in the figure, we have to identify the type of treatment unit processes indicated by various blocks labeled as A, B, C, D and E. So we have different blocks, like A consists of screenings and grid chamber, B has the primary clarifier, C has the secondary clarifier and the aeration tank, D has the nutrient removal and some advanced treatments, and E has some sludge treatment. So what are these processes? You have to identify which one is primary, which one is preliminary, what is secondary, tertiary and sludge processing. Option D. So very direct. So in preliminary, we have the screen and the grid chamber. Then primary treatment, we have the primary clarifier. Secondary treatment, we have the aeration tank, which is typically an ASP. Then for tertiary, we have the advanced treatment or nutrient removal, and then the sludge processing. Right. So very direct. Okay, next question. What does the presence of free ammonia in river water indicate? Okay, so suppose in a river I am finding a lot of free ammonia. So does it represent recent pollution or past pollution or intermittent pollution or no pollution? So when do you think this ammonia can be generated? From where this ammonia is coming? Any idea? Okay, chemical plant, but like ammonia, ammonia formation generally happens when? basically you try to remember that whenever there is some microbial degradation of any pollutant, okay, mostly anaerobic, okay, so in many places there is some ammonia that is coming out. So if pollution is there, ammonia will be forming as a byproduct. Okay, so if it is a recently polluted thing, then more and more ammonia will be produced. Okay, and as it flows with time, more and more time, if aerobic conditions are there, we are having more DO and some nitrifying bacteria are there, then this ammonia will change to nitrite and then to nitrate. Okay, so if I am talking about recent pollution, it the ammonia will be a direct indicator. So always remember that thing. Yeah, chemicals plant, industry, from all ammonia can come. But if I'm talking about a river, okay, if there is some organic matter which is nothing but the pollution and some decomposition is happening, ammonia will be formed as a byproduct. Okay, so that's why we generally denote recent pollution with the help of free ammonia, right? Now the next thing. Okay, again it's a small numerical, not very big problem. So it says that in a water treatment plant, a horizontal sedimentation basin maintaining laminar flow conditions is designed to handle a flow rate of 0.45 meter cube per second. The basin has a rectangular shape with dimensions: length as 42 meter, width as 16 meter, depth as 5.5 meter. Assuming the settling velocity of particles follows type 1 settling, calculate the removal efficiency of particles. Given diameter as spherical of 28 micrometer, particle density as 2.5 gram per centimeter cube, density of water as 1 gram per centimeter cube, dynamic viscosity as 0.01 gram per centimeter second, and acceleration due to gravity as 980 centimeter per second square. Okay, so you have to find out the removal efficiency of the particles. So can someone tell me what are the two factors that we have to find out the removal efficiency? Which two parameters do we need? We need to calculate. Can someone tell me? Then maybe we can discuss the problem till the time everyone else is solving. So when we are calculating the removal efficiency of any system, we have to find two parameters. So what are those two parameters based on these information? Any idea?
Settling velocity of particles and the surface overflow rate.
Yes, definitely. So please try to find out. I'll wait for some time. So first find out the overflow rate. All the informations are given, and then find out the settling velocity. So to find out the settling velocity, as you know, type 1 settling is given, so we can apply the Stokes law. Okay, we can apply the Stokes law. So with the help of that, we can find out the settling velocity. So if you have find out the overflow rate also, you can write it in the chat box. We can check. The answers will be very small, so it will be in 10 raised to power something. If you are converting everything to meter per second, it's better to convert every answer in meter per second. That is the standard unit, so that there will be no problem when we are finding out other parameters. So overflow velocity is 6.7. Yes. Yeah. It is 6.7 into 10 to the power minus 4. Right. What about the settling velocity? Others, you don't worry. If you are not able to solve, I will definitely do this as a practice once, and then we will solve one more problem. So just wait for some time so that others who know, they can try and solve the problem. So please be very careful. Everything is given in centimeter or micrometer, in those parameters. So try to convert everything in meter per second. Then the unit conversions will be easy in the later stage. No answer? Okay, we'll solve. Okay, settling velocity 6.4. Yeah, it is correct. Definitely it is correct. Okay, so now you can easily calculate the removal efficiency. Okay, so we'll see how to solve this problem for others. Till then, you can find out the removal efficiency. So question number 9. So first we'll find out the surface overflow rate. So I will denote it as V or V naught. Okay. So this is nothing but Q by L into B. I told you that you have to say take the top surface area. So it will be nothing but 0.45 divided by 42 into 16. This is 6.696 into 10 raised to power minus 4 meter per second. So very simple and direct. Okay. Next is the settling velocity. So this we denote by Vs. Okay. So what is the formula? It is rho g minus 1 d square by 18 mu. Okay. Direct formula. So here we will put 1 gram per centimeter cube. Okay. Into 980 centimeter per second square. G value is given as 2.5 minus 1, and what is this is gram per centimeter cube, and then we have 28. Okay, I am just writing as micrometer square by 18 into again 0.01 gram per cms. So you have to convert this, all this, okay, into meter. All this you have to convert in meter. So after conversion everything, you will get it as 6.403 into 10 to the power minus 4 meter per second. Okay, this conversion is very important, otherwise the question will be wrong. So what will be my particle removal efficiency? So this is denoted by eta. This is nothing but Vs by V naught into 100. So Vs is 6.04403 and it is 6.696. So this will turn out to be 95.62%. So this is the answer. So you'll get the answer as approximately 95, 96%. Okay, yeah, Haritra is right. I hope everyone is clear. Very simple, direct. Nothing, nothing tricky about this. Okay. So the same thing is given in the detailed solution. Okay. Okay, next problem. In the monod equation, mu represents that substrate okay, I think the answer is already out. Okay, anyway, we'll discuss. Represents that substrate concentration at which specific growth rate is half of the maximum. So you have already seen the answer, it is false. So can someone tell me what does substrate concentration at which specific growth rate is half of the maximum represent? It is not mu, this is false. Okay, but this is also known as something. Can someone tell me what is it known as? You have seen the answer already, that's why I'm not discussing. It is false. But what does it known as? Any idea? What is the substrate concentration called when the growth rate is half of its maximum? So what I am asking is, so as per the monod equation, monod kinetics, this is how you will get a graph. Okay, this is S, which is nothing but the substrate, and here you will have the mu. Okay, mu is the growth rate. So this is the maximum growth rate, mu max. Now it is saying that if at some growth rate it is half of mu max. Suppose it is here. Suppose it is here. So it is mu max by 2. So at this particular growth rate, what is the corresponding substrate? What is this called as? What is it denoted as? Any idea? It is called as, I will write, this is, I have written the abbreviation. Can someone tell me now? No idea? It is called as half saturation constant. It is called as half saturation constant, and it is denoted by Ks. Okay, half saturation constant. Have you heard about this term? Anyone who has heard about this term, or you have not heard at all? Guys, please answer. Have you heard about this term? Half saturation constant? No. Okay. So just remember that. So this monod equation diagram, do you know? Any idea about this? Any idea? Okay, you may be learning later also, but I think it's already there in the lecture. So just make a note that when you are making a graph between the growth rate mu, okay, and the substrate S, okay. So this is how the graph looks. It will first increase and then straighten. Okay. So this is the maximum. and whatever the corresponding to, yeah, so whatever the corresponding S to the mu max by 2 is known as the half saturation constant. So just remember this thing. Okay. So the same thing is here. Yeah, same thing is here. Right? Go to the next question. Again, a very small numerical. Similar type we have already done. The municipal corporation must handle a daily volume of 720 meter cube per day of water. It is found that overflow rate is 16.5 meter per day. Depth is 3.5 meter. Width is 5 meter. So you have to find out the length of the rectangular settling tank designed for the removal of discrete suspended particles. So whatever we have discussed, I think in question number 4, it is just kind of opposite. Okay, in reverse. So please tell me the answer first. You have to find out the length. Very simple and direct. We have already solved this kind of problem in question number 4. On the same parameters, just some other parameter is asked now. Please try to answer. Yes, Haritra, your answer is absolutely correct. It's 8.7 meters. Others, I see only Haritra answering all the questions. Are you people not trying or you are not able to understand? Please try to answer because we are solving similar kind of problem and the same I'm asking again. Okay, so please follow up in the within the class and then you can answer, right? I hope you have a pen and paper and a calculator with you. I request everyone to please sit with a pen, paper, and calculator for each of the problem solving session. If you solve more, then the practice will be there. Okay, so I will just show it quickly here because similar problem was there. So basically, first you have to find out the surface area. That is nothing but the flow rate divided by the surface overflow rate. So earlier we were finding out surface overflow rate from the flow rate and the surface area. Now it's just the reverse. Okay, so surface area is also equal to L into B. So now we know the breadth. It's already known 5 meter and length we can calculate. So very direct. So here the depth information is an extra information. So it's just to confuse you people. Okay, it is not at all required because I have told you whenever we are talking about overflow rate or surface overflow rate, we only need the top surface. That is the length into breadth. The depth doesn't come into the picture. Right? Next problem. Okay. So here again it's a Stokes law question. Here you have to find out the diameter, maximum diameter that can be effectively removed 100%. So all the parameters are given: flow rate, depth of the channel, width, specific gravity, G, mu, everything is given. So find out the diameter. This time I want others to also solve it. So just to give you an hint, first find out what will be my surface overflow rate. Okay. And for 100% efficiency, my surface overflow rate will be equal to my settling velocity. Okay, so equate that surface overflow rate to the settling velocity and then find out the d, the diameter of the particle. Very simple. I think you can do it. If you are not, then we will see how to. Okay, so just I'll wait for 1 or 2 minutes. So what is the surface overflow rate you are getting? Can someone tell me? At least tell the surface overflow rate. Yes, that is correct. So now find out the diameter. Okay, so I will quickly solve this problem. Mm, Question number 12. So first the SOR Q by LB 0.75, 10 into 3, 0.025 meter per second. Now for 100% efficiency, SOR will be equal to my settling velocity. Okay, so my settling velocity will be equal to rho g minus 1 d square by 18 mu. So it will be 0.025 into, oh sorry, will be equal to 1000 into 9.81 into 2.15 minus 1 into d square by 10 into 10 to the power minus 3. Okay, so my d will turn out to be 0.mm. So this answer is in mm. You will get the answer in meter, but I gave it as an mm. So this is how you have to do it. Yes, Saritra, you are right. Okay. Which of the following factors does the sewage load not depend on? Rate of water supply, population growth, infiltration of groundwater, design of sewer system. So you have to tell me which of the following factors does the sewage load does not depend on. Just think about it. Type your answer in the chat box. B. Okay. Any other answer? Just take case one by one. Okay. Think about water supply. Just think if the water supply will, if it increases or decreases, whether it will affect my sewage load. If the population increases or decreases, whether it will affect my sewage load. So actually the correct answer here will be option D, design of sewer system. So just think that if more water supply is there, obviously more sewage is going to come, because around 80 to 85% will turn out to be sewage. Then population, if the population is increased, obviously the water use has to be increased, and then the sewage load will increase. So it will also depend on that. Then infiltration to groundwater. So ideally, the groundwater should not infiltrate to the sewage, ideally. But in many cases where we have a combined sewerage system, okay, or where there are leakages or some other problems, there are chances that the sewage load will increase due to infiltration of groundwater also. Ideally, it should not happen, but there are chances in the case of combined water system, sewerage system, or other cases. Whereas the design of sewer system will not increase the load. Okay. Based on the load only, we will design the system. But it will not depend on the, but like the sewage load will not depend on the design of sewer system. Are you able to understand? Or is there any confusion? Because none of you have answered it as D. Okay. Once we know the sewage load, we will design the sewer system. That is different. But the kind of design we are, what kind of pipes, what is the size, what does not depend on the, like like it will not affect the load. Load will be whatever is happening before that. Okay, we'll move to the next question. Select the correct statements regarding screens and their purpose in wastewater treatment. Screens prevent any interference to treatment. Screens are used to protect process equipment. Screens are a part of secondary treatment. There is no head loss when sewage flows through the screen. So you have to find out which are of these options are correct. So in this question, there can be more than one answer that can be correct. Okay, so you have to identify both of them or all of them. Like, Okay, A. Are others? Any other answer? Yeah, so both A and B are correct. Okay, because these screens will prevent any big size particles, okay, some wooden logs or any other bigger size particles which can affect the treatment system and also the equipments. Because suppose a big wooden log goes and blocks the pumps, okay, it will be a big problem. So that's why they prevent both of them. Whereas screens are a part of preliminary treatment, not secondary treatment. And also there is some head loss when the sewage flows through them. And we have a formula also. We have developed a formula also to find out the head loss through the screens. Okay. So C and D are incorrect. Yeah, this is the formula, right? Moving to the next question. Select the incorrect statements regarding grid removal. So here we have to identify the incorrect. In aerated grid chambers, there are no moving parts below the water surface. A grid chamber is usually installed after primary sedimentation tank. Grid chambers are used to remove oil and grease from the wastewater. The purpose of proportional wear at the end of channel type grid removal is to measure the rate of flow in channel. So which of the options are incorrect? B is definitely incorrect because it is installed before the primary sedimentation tank. Okay. Any other answer which is incorrect? Yeah. So C is also incorrect because grid chambers are not designed to remove oil and grease. Okay. They are designed to remove the suspended inorganic particles. Bigger size, relatively bigger size inorganic particles they are designed to remove. Okay. Whereas oil and grease are removed by using the skimming tanks. So that's why option C is also incorrect. So the same thing is written here. Okay. For a grid chamber, given a flow velocity of 0.45 meter per second and a detention period of 45 seconds, the length of the tank should be Tell me, it's a direct problem. What should be the length of the tank? Flow velocity is given as 0.45 meter per second and retention period of 45 seconds. So what should be my length of the tank? Very easy and direct. Yes, 20.2, 20.25. Okay. So how we got it? We just have to simply multiply. So length is equal to flow velocity into the detention time. So as you can see from the units also, one is in meter per second, other is in seconds. So second will get cancelled. We'll get in meters, that is the length. So very direct. No need to think much. Next question. For a given discharge, the efficiency of sedimentation tank can be increased by increasing the depth of tank, decreasing the depth of tank, increasing the surface area of tank, decreasing the surface area of tank. So how can you increase the efficiency of sedimentation tank? Just think about it and try to answer. Increasing the surface area of tank. Can you tell me, can you explain how increasing the surface area will increase the efficiency? You can unmute and tell me if you want. There is no compulsion. Or anyone else would like to try? Yeah.
Only guess, not clear.
Yeah, tell whatever it is you are guessing. Okay, so overflow reduces definitely. So what will happen if your overflow reduce? Your surface overflow reduces. So how it is increasing the efficiency? Just think in terms of that. So just think that your surface, like I discussed in one of the other problems, like for 100% efficiency, what I want is my settling velocity should be equal to my surface overflow rate. Now, by increasing the surface area, okay, by increasing the surface area, I have reduced the overflow rate. So for 100% removal, I can reduce the settling velocity also. So if I am reducing the design settling velocity, that means that for low settling velocity particles also, it is getting removed. Okay, 100% it is getting removed. Faster ones are definitely getting removed, but for lower settling velocity particles also, those are also getting removed. So if they are getting removed, that means my efficiency will increase, right? If more and more particles are getting removed from the system, my efficiency will increase. So that's how increasing the surface area will increase the efficiency. So how it is linked? Increasing the surface area means decreasing the overflow rate. Decreasing the overflow rate means decreasing the design settling velocity. Decreasing the design settling velocity means we are targeting more and more particles to get settled. So in that way, my efficiency will increase. Is it clear? Okay. So the same thing I have written here and I have explained in simple terms. Right? We'll move forward. The peak factor is given by peak flow into average flow, peak flow minus average flow, peak flow plus average flow, peak flow divided by average flow. We have just discussed this. Tell me fast. Peak factor is given by, so definitely it's peak flow by average flow. Okay. Non-spherical particles will settle dash than the spherical particles. Slower than, faster than, equal or same. So suppose you have some spherical particles or you have some non-spherical particles. Okay. So which will settle faster? You have to tell. Any idea? Option A. So definitely the non-spherical particle may experience more drag. Okay. So there will be some, it will be retarded. It will be getting slower. Whereas the spherical particles can easily go through. Okay. It can easily settle. So the drag will be less. So non-spherical particles will settle more slowly than the spherical particles of the same volume and density for all flow conditions than other than laminar. The drag coefficient is also a function of shape of the particle, which must be determined experimentally. So as I told you, the drag will be more in case of non-spherical particles. Next problem. The degree of treatment required for wastewater depends on raw wastewater characteristics, desired quality and possible reuse of treated effluent, state regulated wastewater discharge standard, or all of the above. So very direct question. It is D. It will depend on all of them. Okay. So how much treatment I want to give will depend on how much input is coming and how much output should go. Okay, what are my raw water characteristics coming and how much and what kind of treated effluent I want to release. So both it will depend on, and what are the discharge regulations. If the government have given some regulations that you have to treat up to this extent, then the degree of treatment will be changed. Okay, so D is the correct answer. Sedimentation tanks are an appropriate example of unit operations, unit processes, both A and B, or biochemical processes. So we have something called as unit operations and we have something called as unit processes. So under which of the category the sedimentation falls? B, biochemical. Is there any biochemical reaction happening in sedimentation tank? Just think about it. So unit operations are those which are generally happening as per physical forces. Okay. Whereas unit processes can be some chemical, biochemical kind of processes can be there. So all kinds of sedimentation are nothing but just settling down based on gravity, based on physical forces. So these are all unit operations. Okay. So treatment units in which application of physical forces predominate are called unit operations. So physical separation of pollutant occurs in these systems, e.g. in screening, grid chamber, sedimentation. So here only based on gravity, the particles are getting separated. Okay, physical forces or some kind of straining like in screen. Okay, so only physical forces are there, no chemical, biochemical forces are there. Can someone give an example of unit processes? What can be an example of unit process? Any idea? like the activated sludge aeration tank. Activated sludge process aeration tank. Okay, it's a example of unit process. Okay, next question. Identify the correct statement concerning advanced wastewater treatment processes. So first says disinfection is typically considered an advanced wastewater treatment process. B. Selective ion exchange is used for the removal of nitrate from secondary treated effluent. C. Both A and B. D. Carbon adsorption is primarily used for suspended solids removal from secondary treated effluent. So which of them are correct? So definitely both A and B are correct, because disinfection, as you have seen in the one of the previous block diagram problem also, the disinfection is an advanced process, okay, after the secondary system. And for nitrate removal, we can use some ion exchange method. Okay, ion exchange, it's a nitrate, so it will be replaced and method can be used. Whereas carbon adsorptions are not used for suspended solids removal. Okay, for suspended solids removal, we basically use, if it's inorganic, then we use the like bigger size inorganic particles like the grid chamber or the primary sedimentation tank. Okay, so suspended particles are taken care in that aspect, or some maybe some filtration processes also. But carbon absorption, we try to remove some pharmaceuticals or some dyes, other chemicals, toxic compounds, heavy metals, like those things. Okay. Yeah, Mohan, you are trying to speak something? Okay. Next problem, intermittent sedimentation tanks. A. Store water for a certain period and keep it in complete rest. Allow water to flow at reduced velocity for a significant time. Are also known as continuous flow type tank, or none of the above. So we are talking about intermittent sedimentation tank. So just think about it, that intermittent sedimentation tank, the water will be in rest or it will be slowly moving. So basically in an intermittent sedimentation tank, the water is in a complete rest and it is stored for in that way for a certain period of time. Okay, so option A is correct, not B, because other, like the intermittent tanks are also called as quiescent type tanks, are those that store water for a certain period and keep it in complete rest. So just remember that. Which of the following is not an assumption of Stokes' law? Particle settling is independent of influence of other particles. The medium is of infinite extent. Reynolds number is less than 10, or flow is laminar. Which of the options are not an assumption of Stokes' law? Any answer? Which of the option is not correct for Stokes' law assumption? Option C. Okay, Reynolds number less than 10. Then what is, can you make it correct? What is the correct assumption, Haritra? Any idea? Reynolds number should be less than what? So Reynolds number should be less than 1. Okay, so that is the answer. For the assumption of Stokes law, we will assume that there is a discrete particle settling. So the particle is independent, the medium is of infinite extent, and there is a Reynolds number of less than 1. If the surface overflow rate of a settling tank is V and settling velocity is U, what will be the ratio of removal efficiency? Okay, having a velocity for of particles having a velocity less than the critical velocity. So we have seen, so it's just a repeated question. So it will be basically U by V. So settling velocity divided by the overflow rate U by V. Okay, so just make a note of it. The type of settling most likely to occur in a real sedimentation tank is, so here we are talking about real sedimentation tank, not an ideal sedimentation tank, but a real sedimentation tank. Okay, so mostly in real sedimentation tank, we tend to see flocculent settling, though we want it to be discrete settling, but mostly in real sedimentation tank, the particle will come closer, mix with, attach with each other, and then settle. So that's why it will be a flocculent type of settling. Okay. Now next problem. Surface loading rate of a 0.02 mm particle is 0.02 centimeter per second. Compute the efficiency of removal of a 0.024 mm particle. So whether it will be 86, 100, 98 or 42. So surface overflow rate is given. Okay. Compute the efficiency of removal of a particle which is of 0.024 mm size. So mind you, here we don't need any calculation. You can just see and tell the answer. No calculation is needed. So can someone tell the answer? B, 100%. Why do you think so? Why it would be 100%? No. So the idea behind is if the surface loading particle is designed for 0.02 mm, so any particle which has a diameter more than that will be definitely be removed. Okay, so that's why the answer is 100%. So all particles having a size more than the size of the particles for which surface overflow rate is calculated are 100% removed. So that is how you have to answer this. Okay, I think this is a very simple problem. We will not see this for the interest of time. Which of the following is not an objective of providing an equalization tank? balance the fluctuation, of concentration, assist in self-filtration, removal of organic matter. So you have to tell me the which of them is not a function of equalization tank. Any idea? Equalization tank. So basically an equalization tank is used for all of them except for the removal of organic matter, because it is just to store the water, okay, wastewater, so that there is no fluctuation in the flow, concentration and kind of self neutralization. Okay, so no organic matter is being removed, right? So that's why that is the correct answer. Okay, so I think we don't have time to solve much of the bigger problems because there is some kind time constraint today. So I'll be stopping here with the discussion. So if you have any doubt, you can tell me now or you can leave for today. I think we have discussed enough MCQs for today. So please let me know if you have any doubts. Anyone? Or else you can leave the session. We will meet again on 18th February, same time, 7 to 9 p.m. on a Tuesday. And this is my contact ID if you want to. In main exam, I think around it will be of 100 marks. So based on that, mostly 1 or 2 mark questions will be there. So some 50 60 problems will be there.